So if you are evaluating this, one, you could just physically plug in a -4. So you could take 13 times base 4 to the power of, use the caret symbol. And then in parentheses, you could plug in the -4 minus 2. So you could evaluate it this way. You put a decimal or hit the diamond button so it displays as a decimal, and you get your answer of 0.0032 approximately. Now, there's some other ways that you can evaluate this, correct? We could just type in our expression, 13 times 4 to the power of, and leave the variable, x minus 2. Use the with key, x equals, and then we substitute in -4. We get the same thing, in decimal form. We could also take our original function, plug it into our y editor, right? We could take 13 times 4 to the power of, and in parentheses, x minus 2. If we enter that, we can see that it's set up in the way that we expect it to look. If we go to our home screen, we can use the function notation y1 of -4, put it in decimal form, and hit enter. So those would be the main ways that you can evaluate that. It's up to you. I don't care how you choose to do it. Okay. Now, when you look at this, when you were evaluating with a -4 here, what you're looking at on this, if I evaluate f of -4 is equal to, I take 13 times 4 to the power of -4 minus 2 is a -6. Okay? When you are identifying growth and decay, which again I'm going to talk about here on a later slide, but I want to introduce it since we're doing these anyway. Okay? When you look here, your initial value was 13, and your new value is 0.0032. So are you expecting that this is growth or decay? Is it getting bigger or getting smaller? Smaller by quite a bit, right? That's what the exponential model is. It's like pretty steep growth or steep decay. Okay? When you're looking at this, if you see that your base is 4, right? But we have the rule, if our base is greater than 1, then we have growth. If our base is less than 1, we have decay. Well, the negative powers come into play here, because if you think of your base using a positive exponent, right? So what we would need to do is we have our 13 times. The negative power is going to take our base and move it from a 4 to a 1/4. So this is actually what that represents. Does everybody see how that's true? So as I go through this, I would just kind of mentally calculate this. F of 1, I'm going to take 28 times 4 to the 1 minus 1 is 0. Anything to the 0 power has a value of 1, giving me just 28. Right? So here we saw that this was decay. Here, our initial value was 28. At this particular case, our value is still 28. So what we have right here is, even though our model for this particular problem, because of that 0, again, it's not specific. It's not a decay model because of the form, but what we see with this particular base when we evaluate it becomes a decay form. This one, because it's a power of 0, becomes just a constant, right? And so here we see that this would be decay or go down. This we would expect it to be a constant, okay, which it is. And then the final one, if we take 24 times 4 to the power of 2 plus 8, which is 10, we can see that that fits the model for growth. So when we calculate this, it should make sense that x times the base 4 to the power of 10, when we put it in decimal form, is 25,165,824. Okay, and so that would be our evaluation when we plug in a 2 for x.